welcome and thank you for joining us for the Pioneering Biomaterials Symposium. This is an exciting time at CCA, a moment of transformation and a new era for the college. With the opening of our new studio gang designed Simpson Family Maker building, all of our programs are, for the first time, gathered together on one campus here in San Francisco. This marks a significant step forward in fostering deeper interdisciplinary collaboration, innovation, and experimentation. It's in this spirit that we proudly present the Pioneering Biomaterials Symposium, an initiative we hope will become a biannual gathering in the Bay, creating an ongoing dialogue on the future of materials in architecture and design. At CCA, we begin our events with a land acknowledgement, understanding it to be a transformative act, one that publicly recognizes our presence on native lands and encourages mindfulness of our ongoing role in colonial legacies. CCA's campus is located in Yelamu, also known as San Francisco, on the unceded territories of the Ramaytush Ohlone peoples, who have continuously lived upon this land since time immemorial. We acknowledge the historic discrimination and violence inflicted upon Indigenous peoples in California and the Americas, including their forced removal from ancestral lands and the systematic destruction of their communities and culture. CCA honors Indigenous peoples around the world, and we wish to pay respect to local elders. This symposium reflects CCA's unique position as a hub where pioneers in innovative technologies, sustainable practices, and material traditions converge. It's a testament to the power of collaboration made possible through our alliance with Autodesk, which was created in 2021, so coming on our 5th year, and our partnership with UCSF Research, bridging education, industry, and scientific research to shape the future of biomaterials. We extend our deepest gratitude to Autodesk, Athena, Rick in the room with us, for their generous support, and to all contributors to the exhibition and the participants in the symposium. This exhibition and symposium were thoughtfully organized by faculty members Margaret Ikeda, Alex Schofield, and Evan Jones, co-directors of the Architectural Ecologies Lab, and Nagar Kalantar, co-director of the Digital Craft Lab, with invaluable support from current CCA Architecture Division students Kira Finnegan, Dawn Lawrence, Fong Tran, and Angie Rosen, as well as recent MAD alumnus Ali Parmigiani and BARC alumnus Claire Leffler. We're deeply grateful to them for their dedication, vision, and hard work in bringing this event to life. At CCA, we believe in learning by doing, in making art and design that matters. This symposium is not just about discourse, it's about empowering the next generation, our students and emerging designers, to engage, experiment, and lead in biomaterial innovation. Tonight, we're honored to open this 2-day symposium with a keynote lecture by Jenny Sabin, a pioneer in biomaterials research and applications. Her talk will set the stage for the discussions ahead. We also invite you to attend our upcoming events. Our next lecture, featuring fantastic local practice Studio Ahead, will be held in this space on March 11th. You can learn more about our events at scaffold.architecture.cca.edu. Now I'd like to, I always get something wrong. You're the participants, the organizers, and the people that made it happen. Now I'd like to turn it over to Margaret and Nagar, who will introduce the event. Thank you again for being here. We look forward to the conversations ahead.
All right, welcome everyone. We didn't know we were introducing the event, but we will introduce the event. We are so happy that you're all here. It's quite an amazing thing. We've been working on this since last a year with Autodesk Research. We have formed an alliance 5 years ago. We went to Rick with an idea, and I just remember at a moment when there was a light bulb that went off, like, oh, might make this work. And that was right during the pandemic. We've had symposiums every year, but this year we're opening our new campus, and we thought this would be the time to make this a more national event, where we could bring together people that we have met through different events, particularly the Biomaterials Challenge, and people we've met through Autodesk Research. And so really, thank you so much. It's a thrill to have you all to be here at CCA. And I just wanted to start by thanking our students, our former students. The people that are listed there are just some of them, but they are really our rock stars. We asked them to, we asked them to participate, and they do it with so much love. We just love our CCA students. They are so talented and so dedicated, and this could not have happened without them, as well as our colleagues here in Autodesk Research. So we're going to introduce, we're so thrilled to have Athena here today, because Athena is someone we've worked with since 5 years ago, and now it's the first time we've actually been here together. So this is Autodesk. It's been an amazing opportunity for us to form this alliance. This alliance has happened from 5 years ago, where academic and industry can meet through the technology centers. And through the residency program, some of our students have become residents and are able to not only use tools there, but you can see we have meetings there. We host ways that we can Zoom in a facility that is, quite extraordinary. So we really appreciate that kind of setting that has set up the kind of work that you'll see today up in the exhibition.
My name is Negar Kalantar, and I'm an Associate Professor of Architecture Division and Co-Director of Digital Craft Lab with Jason Kelly Johnson, that is here as well. I want to talk a little about, the goal of collaboration with Autodesk Research is to move beyond individual research silos. If we want to make a real impact on urgent change like climate change, we must rethink how we design, educate, and build, and that requires collaboration. Bringing together people who share a common goal, what we are seeing today is the evidence of that commitment. We believe the power of education and the significance of the work that we do here. The future needs new designers who think differently, embrace change as a design opportunity, and go beyond individual thinking, and to harness collective intelligence for sustainable solution. Our academic alliance with Autodesk Technology Center highlights our academia and industry that can converge to drive innovation to tackle environmental challenges. This collaboration is crucial for pushing the boundaries what is possible for our profession. I'm honored and happy to have Athena Moore here with us today. Athena is the Network Strategy Manager for Autodesk Research, where she leads the Autodesk Research Residency Program. In this role, and through her volunteer work in cycling, art, and social justice, she had built a strong commitment that support and empower one another. She has been with Autodesk since 2015 and is based in Boston. And her continuous support and creative problem solving and dedication over the past few years has played a critical role in where we are today. We're deeply grateful for having you here and coming from Boston and witnessing what we did together. Thank you, and we're honored to have you here.
Well, I'm going to try to start by not crying, but that was a very nice introduction, so thank you. So nice to see everyone here. Thank you so much for being at Pioneering Biomaterials. I know that we've talked a little bit about how this alliance formed, but it feels really special to be here in person. We started talking about this idea back in 2020, and as mentioned, it was just before COVID. So by and large, the work that we've done together has been in a remote capacity. So it was really kind of sinking in for me yesterday. I was like, it feels so nice I get to be at CCA for this celebratory event. It's our anniversary. It's just pretty incredible. So I want to give you just a little bit of context for Autodesk and Autodesk Research, what we're about. Autodesk's mission is to empower everyone, everywhere, to be able to design and make anything. So Autodesk Research is really driving that mission by looking for opportunities where others might see roadblocks. Autodesk software, our technology spans nearly every industry, so we're looking at architecture, engineering, construction, product design, manufacturing, media and entertainment. And artist research is working across these industries to really investigate and kind of contextualize where our technology can play a role in the emerging challenges that are happening in the design space. So another key thing that we do is work with partners to really develop the sense of shared knowledge and understanding of what's happening in those industries. One of the key ways, I know the research residency program was mentioned, that's one of our key tools for collaboration within Autodesk Research. Myself and my team are responsible for that program. And it's a really interesting opportunity for us to bring innovators in directly and co-explore and co-create what the future of our industries looks like. We bring in a globally diverse range of teams from across startups, academia, and industry. And that's actually where our relationship with CCA started. So it was once just a little residency project, but I think pretty early on we saw this opportunity for a lot of shared value, and we realized we wanted to work more deeply together. So I would say since then, our alliance has become this really transformative partnership. We're really able to co-create interesting work, build out our collective knowledge, gain greater access to diverse perspectives, people, ideas, and also expand our reach, just by nature of having our networks collide in this way. I think it's interesting, I've mentioned Autodesk is across all of these different industries, and our program in particular is looking at all these different kinds of teams. And even with that breadth, I find that it can be kind of it's too easy to get siloed. It's not what we need to do. It's sort of inadvertent, and I think it's natural to be heads down. But it's exciting when we can find ways to kind of back out from that. So that's kind of a core of what our program is trying to do, but it's also, we have such a shining example of that in CCA. We have this partner that it's so exploratory. We are constantly bringing ideas to each other. It's I don't know if we can do that. The answer is yes. But the creative problem solving is very much a shared trait, I would say. And so, to me, that's it's just a shining example of what it is we're trying to do. Again, I think I kind of come at a lot of things with optimism. I know that's kind of a crazy thing to say in this current moment, but I really do feel like we have, kind of regardless of the size of a problem, we have the knowledge that we need to solve it. And so for me, the more interesting challenge is figuring out how do you access those points of knowledge, those resources, and then point them in the same direction. So I think that's what we're doing with CCA. I think that's what we're doing with this event, and it's beyond exciting to me to be here for this. So I'm super thrilled for the next day and a half. And I just also want to thank all the presenters and speakers and attendees and exhibitors and students and everyone who's involved. This was a huge lift. So thank you all so much for being here. And with that, I will hand it over to my colleague, Omari Barron.
Hello, everybody. How's everybody doing? You happy to be here? Yeah. All right. So I had a really long intro for this next person. Let me tell you a little bit about myself. I'm a research engagement program manager for the Autodesk Residency program. I work with Athena. I also work with Nagar and Margaret and CCA students. Just so you guys know, the work that you're doing is very inspiring. Each day that I get to see it, it does inspire me to do more. So don't think that your work goes unnoticed. It inspires most people. So moving forward, I have the pleasure of introducing an extraordinary individual. Her work is reshaping the landscape of architectural practice. Professor Sabin holds the prestigious title of Arthur L. Isabel B. Weisenberger Professor in Architecture and serves as a chair of the Department of Design Tech at Cornell University's College of Architecture, Art, and Planning. It's AAP. Not only is she a leading academic, but she's also principal of Jenny Sabin Studio, an experimental architectural design studio based in Ithaca, New York. Professor Sabin's work is cutting edge in architecture, exploring and fascinating intersections between architecture, biology, and mathematics. This is really short. The accolades that Professor Jenny has is extraordinary. So please give a warm welcome to Professor E.
Wow, this is a beautiful room of people. One second while I switch over here. Great. Well, it's a sincere pleasure to be here this evening. Thank you, Margaret, Nagar, Alex, Kevin, for the kind invitation. It's so great to see former students, current students, colleagues, collaborators. It's just really, really awesome. Thanks to the CCA and also to Autodesk Research for all of your support. So tonight, I'm going to lecture on 3 topics. The first is focused on meaningful and rigorous transdisciplinary collaboration towards a biomaterials and biosynthetic paradigm at the intersection of design, technology, and science. The second topic will focus on how this translates into impactful practice for diverse societal impact and benefit. And the third will focus on how pioneering design methods and technology, informed and inspired by natural systems, produce powerful results, pushing the frontiers of architecture. My talk is framed through 3 distinct domains: learning from nature, mimicking nature, and collaborating with nature. This is the space where design strategies for biomaterials, biomanufacturing technologies, and more broadly, new discourse on what architecture can be emerge. I will elucidate the research methods, prototypes, and architectural projects that I've achieved together with my collaborators and students and beyond, which include adaptive building skins, fabric structures and ceramic assemblies, and architectural interventions that ultimately reconfigure their own performance based upon local criteria and human interaction. I'll talk about several of these research trajectories, but not all 5 specifically. For the past 20 years, together with collaborators, research associates, senior personnel, designers, and students, I've cultivated a working methodology that fuses divergent influences in the form of what I call a biosynthetic design philosophy and a new model for collaboration across design, science, and technology. Indeed, 3D printing, bio and living materials, advanced manufacturing, and robotics are transforming how we live, work, do business, and engage with our communities. I see correspondences between these integrated advancements and our biosynthetic design philosophy, and that all form is rooted in the intricacies of process between part to whole, as informed by connectivity, communication, and context. In the first domain, I will discuss the foundation for my collaborative work and how nature as a teacher has impacted my thinking, teaching, research, and applied practice. Here, we learn specifically from cell and biological systems to produce ecological design models and material analogs for reciprocal and bio-informed processes and thinking in design. As has been mentioned in the introduction, to address today's pressing issues in our built and natural environments, scientists and architects and designers and beyond must embrace change and cultivate new collaborative design models to comprehend key social, environmental, and technological imperatives. And I might say that in our current context, this work could not be more pressing. This requires a radical departure from traditional research models in architecture and science, with a move towards hybrid, transdisciplinary concepts and new models for collaboration. One approach entails the hybridization of labs and studios to fusing innovations across science and architecture to fabricate next-generation architectural materials and structures that are adaptive, sustainable, and resilient. This is a photograph taken on the first day of a course that I co-taught with a longtime collaborator, Dr. Peter Lloyd-Jones, who was a cell and molecular biologist. The course was titled Nonlinear Systems Biology and Design, and we taught it in the Department of Architecture, then at the Weizmann School of Design, which was formerly known as Penn Design. This was taken, I believe, in September of 2006. And one of the things I wanted to mention in the formation of Lab Studio, which we've been told was one of the first models for a truly hybrid research and design environment shared between architects and scientists, is that before we began to formalize our collaborative research, Peter and I took a full year to simply learn how to communicate with each other. And so he would engage in my studio reviews, I would engage in his weekly lab meetings. He was completely freaked out by the culture of the critique. He thought we were just horribly mean to our students to put them in front of large audiences and have them communicate on their design projects. And in turn, I had to let a lot of information sort of pass over me to focus in on the key systems that Peter and his team were exploring. And there's some important people in this image. I might mention that Erica Sabin, who's featured here, graduated with her MArch, and we co-advised her thesis, both myself, Peter, and eventually Xu Yang, who's a materials scientist at Penn. And she went on to do her PhD in cancer biology at Stanford. So one of the seminal references for this work is the biological extracellular matrix, which is a dynamic protein network that physically and chemically couples the exterior environment of cells with their interior and vice versa. This matrix environment is a cell-derived, woven, and globular protein network that contacts most cells within the body. One could call it an architectural textile of sorts. So the big idea here is that half the secret to life resides outside of the cell. So you have DNA or code, but that code is acted upon by external environmental events. So essentially, we were looking at the role of context in dynamically specifying form, function, history, event, geometry, pattern, and beyond as a set of powerful ecological design models to bring back into architecture. So one of the things, and this was again in the context of Lab Studio, that I quickly realized is that we were able to bring not only our thinking to these questions and problems on the scientific end, but also key technologies to begin to visualize data, to spatialize data, to bring new models, dynamic models, parametric models into the lab context. And so I was actually quite surprised by what wasn't happening in the context of the lab. And so visualization and spatial modeling of data allowed for an immediate bridge with the core scientific work. And as we were beginning to develop these models, we were also dialing in dynamic feedback mechanisms, again, looking at this dynamic reciprocity between environment and form over many iterations across scales, including human scale data scapes. This is branching morphogenesis, which was on view at SIGGRAPH in the Design and Computation Galleries in 2008. And the three topics that we were exploring included motility, or how cells move, surface design, primarily in pathologies such as breast cancer, and certain lung pathologies, including pulmonary hypertension. And so what you see here are two multicellular acini structures, and one is in a healthy condition, which we can see here, and this one is undergoing tumorigenesis. And in the context of Peter's lab, what they were demonstrating in silico is that by changing the architecture of the environment, not attacking the cell, that you could actually return these multicellular structures that were undergoing tumorigenesis or diseased back into a healthy scenario, which as an architect, together with my students, absolutely blew us away. So these outputs now look quite dated to our sophisticated digital eyes, but much of this work also led to a deeper understanding of cellular surface design and morphology. And importantly, the material world that this type of research interrogates reveals examples of nonlinear fabrication and self-assembly at the surface and at much deeper structural levels. In parallel, this work offers novel possibilities that question and redefine architecture within the greater scope of generative design, sustainability, and fabrication. So this mode of working has contributed to a body of fundamental research and also applied projects in my practice that integrate science, technology, and architecture through methods and tools that emphasize design research as a continuous and emergent process. And at a time of ecological and socio-political catastrophe, grounded in our deeply entrenched misconceptions of human and cultural dominance over nature, biosynthetic architecture has the potential to open new models and approaches to how we teach, how we research, and how we practice. We focus on the contextual and material and formal intersections between these fields to innovate responsive and non-standard building skins, biobricks and tiles, and sentient spaces that are not only performative, but also generate what author Jenny Odell calls, quote, attention-holding architecture, end quote. For example, one of the fundamental questions that drives all of the research is how might buildings and their integrated material relationships behave more like organisms do, responding and adapting to their local built environments. In this scenario, generative design techniques emerge with references to natural systems through transdisciplinary translation and analogic modeling of biological behaviors and processes such as flexibility, adaptation, and growth into the realm of architectural application. We integrate the premise that nature is resilient, not necessarily efficient, at least in our definition of efficiency. And we also embrace transdisciplinary design with a focus on problem and knowledge generation over immediate problem solving. Yes, we solve problems, but as part of our process, we allow those problems to emerge. And this is done through a collaborative space where there's a shared and mutual sense of trust and the development of processes that are equally emergent, transforming, and evolving. And with strong links between my lab, which is at Cornell, and my practice, the driving mission behind the work is to create resilient, science-driven, and transformative spaces with and for diverse communities. Importantly, this interest probes the productive tinkering and misuse and frequently breaking of digital fabrication machines found in other industries outside of our environments. We produce a lot of what I call productive failures, many more than the final successes. And these issues are informed by issues of craft and making to produce a biosynthetic material set of systems and software design tools that hopefully, or at least as we aim, have the capacity to embed expressions in our built environment. Biosynthetic architecture features adaptive and resilient material applications through the intricate symbiosis of technology, biology, human participation, multi-species participation, and design. Importantly, this work also impacts the science. This is done both through data visualization, as I mentioned, spatial modeling, and advanced manufacturing, and leveraging design as a bridge, including 3D printing, ceramic biotiles that also make impact across engineering and the sciences. So in discerning which effects and materials are actually scalable over the years, we have framed 3 distinct phases. We typically start with the development of new tools to model behavior. That might be based on a particular data set coming forward from one of my collaborators' labs, or a mathematical concept or a set of material behaviors. Some of those tools are then brought into the realm of architectural prototyping, so productively starting to negotiate the problem of scale, and this is where we integrate digital fabrication processes, robotics, and beyond. And then finally, some of these successful prototypes are brought into the realm of buildings and the built environment. So this is purposefully a slow process to work in a rigorous fashion, to make discoveries along the way, and also, as I mentioned, to meaningfully grapple with the problem of scale. Not all of these systems are actually scalable towards architecture. In moving from learning from nature, the second domain focuses on mimicking nature, or the transfer of material and geometric properties and characteristics present in natural systems, such as the beautiful wings of the blue morpho butterfly, into new responsive and programmable material systems that are scalable for architectural applications. This also engages programmable and adaptive materials and the concept of personalizing architecture. I haven't talked about eSkin for a number of years now. This was our first successfully funded National Science Foundation grant. We received this multi-million-dollar grant in 2010, together with Xu Yang, Peter Lloyd-Jones, and colleagues in mechanical engineering at Penn. So this is when I was teaching at Penn before moving to Cornell. And in the eSkin project, our emphasis rests heavily upon the study of natural and artificial ecology of design, especially in observing how cells interact with pre-designed geometric patterns, and how these patterns in turn generate new surface effects. I mentioned Xu previously. We met in, I think, 2006 at the University of Pennsylvania, and Xu is engaging in biomimicry in the true definition of the word, to extract rules, principles, and characteristics from nature, and to then design and engineer entirely new materials that are programmable. So we were working with this notion of dynamic reciprocity, right? So go back to what I was describing with some of those early data sets where we were observing the extracellular matrix and its impact on the formation of morphology and change over time. And what we proposed to the NSF was to develop adaptive and responsive building skins that could change over time. And so we started, at least for the first 2 years, by plating human smooth muscle cells, which you can see here. This is one of Peter's cells, onto Xu's substrates. This is an organic polymer, a PDMS polymer. And we were helping to design and fabricate these polymers. We spent 2 years on grids. We finally got to move to wrinkles. It's a slow process. But what you can see in this image is the cytoskeleton lassoing up and around these pillars, the nucleus stained in blue through confocal microscopy. And what we were interested in was looking at how changes in compliance and geometry and materiality, et cetera, in this simulated environment would in turn alter the behavior of the cell. And so you can see the radical difference between moving from grids to wrinkles. And this was a stand-in for eventually our development of sensors and imagers and adaptive skins that could respond in real time to external stimuli. So the project harnesses tools and modes of design thinking and applies them towards the design and engineering of passively responsive materials and sensors and imagers. There were many parameters that we could have considered, way too many, especially at the beginning. And so we decided to focus on structural color and then dynamic switching from opaque to transparent. So how do we do that? So this is an example of a predefined geometric pattern that's embedded within a shape memory polymer material, and it's displaying structural color change. undergoing deformation and recovery. And so basically what's happening when we would stretch one of these PDMS substrates, all of these pillars, which you can see here, which started out normal to that surface, would then change their orientation. And at a nanoscale, at that wavelength of light, that would dynamically change either color in terms of gradient or a switch from opaque to transparent. And we, so human perception is important, perceive those changes. And so we were really interested in how we might bring that back into architecture in a scaled way. So imagine if you could generate a window on demand, right? To begin to personalize and to tune and adapt your own environments. So we developed a series of prototypes. And one thing I'll mention, most of my collaborators engage in fundamental research. And it's not that they're not interested in application, they just don't do it. So as the architect on the team, I'm constantly pushing scalability. We had proposed to the NSF that we were going to develop building skins. And for Shu and her group, a little tile of e-skin, about this big, was huge in scale for her. And I'm like, Shu, we proposed to the NSF to do building skins. What are we gonna do here? And so prototypes became really important. So we're in that middle phase. And this allowed us to explore the possible features and effects of e-skin, and in this case, at the scale of a facade unit. And at first, we simply simulated both the digital and real-time and interactive possibilities, working with actual data sets, creating our own rendering engines and interactive simulations. We also worked across scales to look at color changing effects and efficiency calculations of that, and then eventually produced a full-scale prototype. And this prototype, which is now in the permanent collection at the FROC in Orléans, it was originally part of the 2013 Archilab exhibition, took us 2 years to develop between the lab, bench side, and the studio. And I should mention, if you're interested in taking a deeper dive into this project, we have several published papers, both on the scientific end and on our end in terms of design and fabrication. And just very quickly, this is Shu's hand passing in front of it. There's an array of sensors, which then trigger a low voltage to a series of components, that the sensors detecting a change in light intensity. And in turn, within the ITO components, which include 2 sheets of conductive glass, a solution of nanocolloidal particles, the packing of those nanocolloidal particles change, and in turn, we perceive a change in color or a dynamic switch from opaque to transparent. And so this was our original vision in terms of how this could be scaled. Imagine a building skin that would dynamically adjust with the path of the sun, and so on. And we're currently looking at possibilities with thin film technology, with industry partners such as Kodak, based in Rochester. They still have really innovative material science teams, really pushing the boundaries of what's possible. So in my practice, running concurrently with this research was the development of Polyform, and this was commissioned by the College of Human Ecology on Cornell's campus. And the project integrates, importantly, both environment and community through advancements in computational design and also digital fabrication techniques. And we were deeply interested in how this might generate a responsive and ornamented architectural intervention to inspire moments of pause and wonder, to inspire moments of gathering and reflection on a busy campus, within a busy campus environment. So this project really allowed us to kind of test what we were doing in the lab in collaboration with Shu and her team and Peter and the engineers in a scaled way. And so structural color in this case is achieved with a dichroic or wavelength dependent thin film that's laminated to tempered glass panels. And so light reflecting from and refracted onto the film changes color and grows warmer or cooler, more opaque or transparent. And of course, is not based on pigment, but on how the film selectively interacts through interference or reinforcement of certain wavelengths of light at a microscopic scale. So a key component of this project is how we perceive subtle changes of light and color within the material itself from day to night. These are some images when it opened. So this project started in 2013. We're about 3 years into the eSkin project. This finally opened officially in 2021. We did have the pandemic in that, but this project was actually, it really took up speed during the pandemic. I think in hindsight, it would have been much quicker to build a building on Cornell's campus than to produce a project that wasn't quite public art and wasn't quite a building, but somewhere in between. And just a little side note, the permit in New York State for this project, Polyform, is for a shed. So in this work, as all of you know, you have to be a little bit of a magician in getting the type of work that we do into the built environment and getting the key stakeholders and partners on board with your journey. So in addition to designing at the architectural scale through demonstrator projects and experimental prototypes that feature responsive and at times adaptive materials that engage with structural color, we also frequently design and fabricate environments that change and respond to dynamic data sets in real time. I'm not going to talk about this project in detail, but I thought I would show one image because it's close to your home here. This is sited in the new Google Bayview campus, designed by Big and Heatherwick Studio in Mountain View. And this is a tower called Eddy, and there's also a project that envelops a stair, which was permanently installed a couple years ago and responds in real time to environmental data within the local biome there. So we also work with non-standard components to investigate the rapid manufacturing of full-scale 3D printed parts for larger architectural assemblies. And I'll just briefly mention some of the origins of this work. In 2009, we received a research grant from the Provost's office at Penn, and this was in the context of Lab Studio. And we were interested in using the 3D printer not as a representational tool, but as a way of rapid manufacturing parts and to explore part-to-whole assemblies. And this was a Z Corp 510. I finally had to get this up. Virginia, where are you? In fact, I met Virginia and Ron for the first time through a shared connection with Mark Ganter at the University of Washington. He had published a little article in Ceramics Monthly with a recipe for printing with clay. And as a former ceramic artist, I have a BFA in ceramics. I suddenly realized during one hot, sticky August in Philadelphia, while we were producing these prototypes from data sets coming forth in Peter's lab, that I could bring this literal knowledge of clay into a new context, a body of knowledge into a new context. And so I took out the proprietary media and mixed up our own bucket of high fire dry stoneware clay body with a little bit of fiber and sugar, took out the binder and put in alcohol, and we were able to produce these parts, which absolutely blew me away, that we could 3D print clay components. And so here you see the same part printed in the regular media, and here printed and fired in our clay recipe. So it's been bisque fired, chemically changed to ceramic, and then glaze fired. So suddenly we have material properties like shrinkage that we need to begin to dial in. So as with a lot of our research, new strands and trajectories emerge through core projects. And so this has led to a series of seminars, studios, and option studios on digital ceramics that represents over 15 years of research and teaching on the subject. And in my lab, we've primarily focused on bricks. I thought that the brick was a good object to begin with. It's an accessible object. Everybody knows what a brick is. And over the years, we have moved from Polybrick 1.0 to Polybrick 2.0 and beyond. And Polybrick 1.0 really was focused on figuring out how to leverage the printer to produce porous bricks, to think about the possibility of mortarless connections, and to also consider the novelty of working with bricks where every single brick could be different, but as long as there was a cohesive strategy for how they connect, we could really kind of push the boundaries of what was possible. With Polybrick 2.0, we opened up a new collaboration with Dr. Christopher Hernandez, who is at Cornell, and he's a mechanical engineer with expertise in the mechanics of bone. And we thought human bone was a pretty cool model to look at for optimizing for load path, to consider the paradox of building with holes, which you see everywhere in nature, to create incredibly lightweight and robust brick components that can then be potentially applied in different scenarios. So why should we look at bone? As we can see in the work of my former student, Begum Birol, who also has work on view in the exhibition, bone is highly adaptive to habitual loading. And this is particularly present within the cancellous trabecular core of the bone. And so basically, if we were to look at a CT scan of the cross-section of a runner versus a bicyclist versus a swimmer, the density of that bone would look very different. And this is an anisotropic, heterogeneous lattice structure that undergoes adaptive and cyclic processes of regeneration. So the lattice undergoes constant evolution guided by its loading conditions. And again, we thought this was a really amazing way to analogically begin to explore how we would optimize for load conditions. So imagine a brick wall composed of Polybrick 2.0 units, where at the base you could have incredibly robust units, but as it moves up the wall, it could become increasingly more porous. So natural load-bearing structures are characterized by aspects of specialized morphology, they're lightweight, they're adaptive, and they engage in a regenerative life cycle. So Polybrick 2.0 essentially aims to learn from and apply these characteristics in the pursuit of revolutionizing ceramic load-bearing structures. So we worked across multiple scales and also across multiple 3D printing techniques and methods. We collaborated with our colleagues in engineering to do analysis and demonstrated through the analysis that these porous brick units were much more robust than solid brick units. And in Begum's thesis, which is now published, we then began to scale into robotic multi-axis 3D printing, which then led to a set of really innovative tools and methods for custom G-code to deal with gravity, bridging, adding additional mesh or material that translated to material to deal with these inconsistencies in real time. And these are some of the final prototypes from Begum's project that emerged over the course of a little over a year. So suddenly we can reconsider what a brick is, what the shape of a brick is, the scale of a brick, how one brick meets its neighbor, and so on. In other projects, we also looked at plants, such as the pitcher plant, to extract design drivers based on superhydrophobic and superhydrophilic characteristics and properties. And this is Polytile 2.0. And so in this image, what you can see is the micron scale texture that we extracted from our analysis of the pitcher plant to generate tiles at scale that were super hydrophobic. So you can see how these water droplets are pooling in these little dimples. And this is the same tile now at 90 degrees, holding these little water droplets in perfect formation. The really exciting part of this project is that we're working at the scale of a typical tile. So imagine a tiled wall where you could direct water for passive cooling, or direct water for green materials, greening building units and facade skins with these tiles to selectively cater to water that's traveling across the tiles. So this third domain looks towards collaborating with nature. This work is focused on both biodesign and biomanufacturing, and literally working in collaboration with natural systems to open up new opportunities in the context of sustainability through living materials that are adaptive and cyclically engaged with their environments. This affords new opportunities to shift away from, for example, materials made from petrochemicals to biopolymers. Within this third stage of work, we collaborate with biological and environmental engineers and other colleagues in chemical and biomolecular engineering to literally design new living materials and explore biomanufacturing opportunities. The project that I'll present tonight focuses on the question, how might we rethink building materials through 3D printing and biologically informed design? And Polybrick 3.0 is a multi-year collaborative project together with my colleague Dan Lau, who's in biological and environmental engineering at Cornell. So in this project, we're looking at possibilities of bioinformed thinking, which is expanded to designing with life through DNA-steered ceramic materials and living glazes. So in the first phase, we primarily focused on programmable biofunctionalities and specifically controlling the emission of cell-free light. So we're developing bioglazes with DNA that are cell-free. And Dan Lau is an incredible scientist. He's incredibly creative and has done pioneering work with 3D printed hydrogels infused with DNA strands. So we're reflecting upon new questions of adaptive and live materials through the integration of advanced processes, both in 3D printing, alongside cutting edge research in DNA hydrogel development. So the prototypes utilize 3D printed clay, hydrogel, and synthetic DNA. And so we're exploring programmable biofunctionalities towards the aim of constructing architectural environments through the development and advancement of these biotiles. So DNA, which is the information storage molecule for biological systems, is also a known material for engineering. So the first phase of this research uses DNA to design with light, where unique signatures fluoresce within the polybrick clay body. And specifically, we're working with a DNA sequence that's based on the luciferase, or the magical firefly. The input energy is ATP, and the output energy is light. And this enables cell-free production of light on ceramic tiles. In polytile 2.0, so we're going back to the tiles, these are not super hydrophobic, but we're taking this to the next level in that we're, again, working at the typical scale of a tile. This is essentially 5 inches by 5 inches. And so we're integrating selective patterning techniques to tune surface conditions and effects at both the micro and macro scales. And looking at the possibility of living walls that not only alert you to local contaminants or particulate matter in the local environment through the emission of light, but then can potentially clean that local environment through chemical and biological interactions. And here we see how DNA nanotechnology can open new possibilities for creating nano to macro scale materials that dynamically react to environmental cues and interact with biochemical and even human reactions. So again, this notion of dynamic reciprocity between environment specifying changes in these surface techniques and responses continues to hold as a very strong theme and driving set of topics. So our current phase focuses on response to the local environment. These are some of the more recent images of the tiles with Dan Lau's DNA hydrotone. So in this last applied project, this work builds upon over a decade of work testing how these biologically informed concepts and adaptive materials can be applied experimentally in architecture and, importantly, engage diverse communities. Specifically, we are working with current technologies, with artificial intelligence, with a focus on these two questions that you can see on this slide. Since 2012, we have been able to deepen and apply our ongoing research on responsive materials that engage the dynamics of light and energy, such as structural color, as I talked about, through high-tech solar active and photoluminescent responsive fibers, which commenced with the project MyThread, which was a commission for Nike FlightNet Collective when they launched their new technology, FlightNet, which we're all familiar with. So following several projects, including Polythread for the Cooper-Hewitt Design Triennial in 2015, we were able to take this work to an urban scale with our winning entry for the Young Architects Program, Lumen, in 2017. I'm not going to talk about this project in detail. I've lectured on it many times, but I will linger on it for a moment because I'm still recovering from it, both physically and financially. Yeah. I loved doing this project. It was a game changer for us, really. The project featured over 18,000 square feet of digitally net porous canopy structures, 3 42-foot tall tensegrity towers to add just yet another level of dynamics to the project, an interactive misting system, robotically wound spool stools, and for the first time, we were able to test our high-tech responsive fibers and knit material system, which, by the way, I've been collaborating with Shimaseki since the Nike project. They're at the forefront of whole garment knitting or CNC knitting, which essentially allows you to shape and knit in 3D with seamless components. And so this was the first time we were able to push both scale, but really push the fundamental research into a large urban environment and the changing conditions of the local site. This highlights how we engage with the local context. So the two canopies stitch into the existing matrix of concrete walls at MoMA PS1 in Long Island City. And alongside that, the pattern drawings that were used to seam and finish the canopy structures. At the time, I was working with Daisy and Fabrics, and we literally produced a 1-to-1 scale drawing through tiled plots that they then used to check their sewing and finishing work. They like to say that they started on the West Coast and ended on some details of the tensegrity towers and some images as it was opening. Everybody loved the cones. There's something about the cones. Like, they really loved the cones. Every Saturday during the warm-up events, over between 5,000 and 7,000 people would enjoy Lumen as a backstage to incredible DJs and artists performing. And this was also the first time that, through our project, I had evening events because I employed a lighting system that would actuate the materials in the evening hours, which was super exciting. In a recent project for a really amazing developer, Imcan in Abu Dhabi, they're really invested in public space, which is something that doesn't get celebrated much or produced in the UAE. We designed and produced a permanent public beach activation project. And this time we were able to collaborate with Gore to develop an entirely new photoluminescent PTFE material that could withstand the extreme climate of Abu Dhabi, including sand and windstorms. This is pearl. So our collaborative work also includes a significant human component, both in how it's made, through a hybrid of analog and digital design processes, and also importantly through active engagement with communities in architectural and urban contexts. And we frequently move back and forth between very rapid digital techniques and methods and modes of making, as you do here. And then we also shift into very slow analog production, frequently with our collaborators and industry partners. And the last project I'm going to show, I'm nearing my time here, is another project by Jenny Sabin Studio that builds on this foundation and is a collaboration with Microsoft Research, which also co-evolved, importantly, in a transdisciplinary context. And in this project, in terms of the domain collaborating with nature, we're literally collaborating with human data in real time to spatialize and materialize changes in emotive states. So in starting this project with Microsoft Research, at the time it kicked off in 2018. I had not worked with a big tech company before. I was a little nervous, but it ended up being just an incredible collaboration. And we knew that we wanted to do something around artificial intelligence, but to really sort of open up the space for a possibility around spatializing the use of AI through a trajectory that would essentially make the technology fundamentally human, to put humans at the forefront of some of the questions that we were posing, and also importantly, to discuss issues of bias and privacy around personalized data sets, and to explore through a demonstrator project how we might begin to leverage these tools to design with phenomena through material and space and form that we've never been able to design with before. So in many ways, the spaces and environments that we inhabit influence how we feel and how we act. And so working closely with researchers and engineers at MSR, ADA, which is the name of the project, is driven by both individual and collective sentiment data, which is collected in real time and housed within the Microsoft Research Building. It's still installed and being used as an active research platform. It's named after the polymath mathematician, first computer programmer, and the early innovator of the computer age, Ada Lovelace. And this video just highlights part of our process, both in conceiving the project and finally installing the project. The project features a lighting system and materials that create essentially a cyber-physical architecture that responds in real time to human participation through the collection, as I mentioned, of both individual and collective sentiment data. This data is processed by AI algorithms and transmitted as sentiment through light and color. And just a little bit of details on the brain ring, which is at the top of Ada. There's a PC on site, and the PC software continually queries data from the network of cameras and through also a connected set of Raspberry Pis in the brain ring. And the PC software continually queries data from the network, from the MSR cameras to analyze user facial expressions. And so essentially you could read the room on a daily basis, a weekly basis, a monthly basis. You could read the entire building annually, go back in time, and beyond. So an important aim of the project is to expand and inspire architectural engagement with humans. And so while AI in this sense powers the project through the precise narrowing and statistical averaging of data collected from individual and collective facial patterns and voice tones, the architecture and the material of Ada augments emotion through aesthetic experience, and thereby hopefully opens the range of possible human emotional engagement. And in turn, the project importantly opens new pathways for fundamental research on the use of AI to correlate connections between human sentiment and local environment. I was able to work closely with Daniel McDuff, who's a researcher at MSR, and he's working on projects that look at how our environment influences aspects of health and wellness. And through the use of AI, one can detect subtle changes in your facial pattern recognition data that can give us some clues that we may not even be aware of how our environments are impacting us. So personalized architecture in this sense detects subtle changes in human emotion through sensors and interfaces that detect changes in facial patterns and voice tones and respond in ways to increase well-being and promote healthier environments. This image just highlights some of the diagrams for the pipeline for the lighting system, which is a 3-tiered lighting system, which includes a network of car lights, an integrated network of LED strips within the digitally knit exoskeleton. And we also produced for this project a custom tensegrity cone in the middle that features a fiber octave sleeve, where we were able to fine-tune and program the lighting relative to the changes in data in real time. And some images of the opening at MSR. We were fortunate to open this in November of 2019, just before the onset of the pandemic. And this group had just figured out if 6 of them started smiling and laughing, they could change the entire sort of experience of the project. So in a way, as a demonstrator project, Ada offers an interface for personalizing architecture to make it more human and reflexive. And importantly, to open questions around the use of personal data sets in these settings. At the same time, Ada expands human emotion through beauty and materiality. It's a demonstrator project showcasing the capacity and future of architecture to hopefully promote and increase well-being through the direct engagement with the spaces that we inhabit. So the title of my talk, Biosynthetic Architecture, is fundamentally about connections and synergies across science, technology, and architecture, steered by the systemic and relational conditions of life, from DNA to sentiment as future adaptive and intelligent materials, and the optimism of possibility. So I don't work alone. I've said we, I think, for the entire talk. I work with some incredible students and colleagues and collaborators, both in my lab and in my studio. And we've been fortunate to receive a lot of incredible funding, generous funding over the last 20 years from industry partners, including Autodesk, thank you, and sponsored research from the National Science Foundation, the NIH, and beyond. And for any undergraduate students in the audience, or if you're a graduate student and you want another master's degree, this is a plug for the new Multi-College Department of Design Tech that I am the chair of, together with an incredible inaugural faculty and visiting faculty. I think Laura is in the audience. We were just teaching studio yesterday, I don't know. But this will take you to the site, which I'm really proud of this. Because, you know, I could have continued to do my work, incredible work with colleagues across disciplines, but through the support and tireless effort of faculty in these colleges and various departments, participating deans, our university president and provost, we've now created a model to really sustain this long term. And in a couple of years, we'll be launching a PhD program. And we're hiring every year for the next several years. So with that, I will conclude. Thank you.
So we're going to do a Q&A. Let's hear it again for So we only have one mic, so put your hands up if you have a question. Whoever's closer gets it first, and then I'll hand it to you. But I have a question. I'm always curious of the spark. Like, what sparked this journey? I know it's a general question. I know.
No,
But
it's a good one.
It's what sparked it and what keeps it moving? What keeps you on this journey?
Yeah, it's a great question. Well, I think early on, and this is why I left my ceramic art practice and decided to pursue my graduate degree in architecture, is that I just was trying to find that model or that space that would bring together my interests and talents in the design arts, interest in technology, and the sciences and mathematics. And so I think there's that driving interest in working across disciplinary boundaries, but also in the context of the early work in Lab Studio and now together with my collaborators at my lab at Cornell, a realization that design has value in other fields, and that's only becoming increasingly more relevant, especially as we face the pressing questions and problems that we encounter now, and that's super inspiring. Like I mentioned, in the sort of early days of Lab Studio, we were producing those visualization models and spatial models to look at data in new ways. The 3D printer was really initially about, what if the scientists could hold their data? Wow. Like, then they could project into their science in a new way. So a realization that I, as an architectural designer, together with my students, could bring value as not only a way of thinking, but also through our techniques and tools and methods. That was a real spark. And so operating as a designer on cancer research, like, it was like so humbling, is of equal value to being able to produce projects like Ada with Microsoft Research.
Oh, you're closer.
Hi, thank you for the presentation. I am curious, throughout the projects that you presented that combines architecture with synthetic biology or where a lot of knowledge in the biology side is needed. I wonder, your students in architecture, what role are they playing in the projects? Is the computational design side, or like how much do they get into the wet lab experience or into the understanding at the molecular level what's happening to be able to really collaborate with the scientists and be able to come up with all this amazing work? So I just would like to hear a little bit more about that. Thank you.
Yeah, thank you. I should mention, I wasn't sure how this was going to go. I'm operating like 4.5 hours of sleep. There was some weather between the East Coast and here. Wow. So for me, and also together with my collaborators, we have from the very beginning focused on bringing our disciplinary expertise to a shared table with material scientists, biologists, engineers, mathematicians, physicists, and beyond. And importantly, not to turn scientists into pseudo-designers or designers into pseudo-scientists, but to create that magic that happens when you bring brilliant minds together from different disciplines. And one of the misconceptions that my students frequently have is that they need to know everything, and they're just like, how do I know the science well enough to do that, or how do I know how to code well enough to do that? And I would say, no, you bring your expertise to the table, and through that, there will be co-learning that happens. I have chosen, together with my students, and there are different paths, to not engage with moving into the wet lab, right? But to work with material scientists and biochemical engineers, as a designer, as an architect, but they do the science and we bring our expertise in design, whether that's through techniques and methods for modeling or helping to guide experiments. But the roles are understood and also shared as within a collaborative space. So essentially, my students are not going into, say, the labs of the material scientists and working side by side on the experiments, but they're working side by side in terms of how they bring their expertise in architecture, or in the case of design tech, we now have students that are coming from backgrounds in industrial design, interaction design, information science, etc. And bringing that expertise to a common question or to a common set of shared problems. And maybe the last thing I'll say is that there's a new institute at Cornell called the Engineered Living Materials Institute, and that's a network of faculty across multiple disciplines and departments focused on the most cutting edge scientific research, but also potential applications for living to near living materials. And we do have some faculty from design that are now working in wet lab space and working alongside scientific colleagues in that context. I hope that answers the question.
We have a couple questions over here.
That was a lot. That was amazing. Thank you very much. Just trying to keep up. I kind of have two questions. One, and they're both related, but I'm really interested in this interaction, like how spaces interact with us and our human nature and how we support each other in those spaces, and the built environment and otherwise. So my questions are twofold. Number one, what's your take on why it was so fascinating? Everybody loved the cones. Everybody wanted to be in these little things. So that's number one. And number two, how do you see this ADA project kind of broadening to the structures that we inhabit in the future? Because it does seem really promising, like understanding the interaction.
Yeah, thank you for your great questions. So the cones, I didn't mention this, but there's also the fact that the work at the scale of Lumen, that there aren't hard edges or borders. It's fuzzy. It's constantly transforming. One's experience was different from day to night. There were, different scales of interaction. Materiality in the case of Lumen and the other projects is not something that's just about the materials responding. It's co-produced by people's engagement, including birds. Birds loved Lumen. It became this aviary. It's just like they were flying through the holes and it was just amazing. Some people call that biophilia. So I think there's something to this architecture that resonates with people. And
Closer to nature?
yeah, it's not a direct, by any means, translation of a cellular form into an architectural form, but there's a synthesis, a biosynthesis of an understanding of a set of relationships across scales, from surface design and change in morphology to responsive materials and beyond, that people really deeply respond to. And also, I think, juxtaposed to the concrete and the Cartesian ordered conditions of the street. And I wish I had done actually a proper post-occupancy analysis of Lumen, because I had so many people come up to me and say, oh my God, I come to this project, every week to take my lunch, or I wish this project was in my child's playground, or I wish this was in a hospital. And that really excites me, especially in terms of where we're going with the work in my practice. And the second question, we with Microsoft Research in discussion, they were at the time doing a big capital improvement project, expanding the campus in Redmond, Washington, talking about how we could take the same material system and integrate it into a facade. Then the pandemic hit, and I need to get in touch with them again. But it can really work, like that we can take the same system and have it situated in like a sort of double glazed context and have it engaging both, on the interior in terms of, again, considering personalizing one's environment, and then also the exterior. So that was one way we were thinking about it.
Professor, you have one more question?
Yeah, we need more. That's fine.
Hello, thank you for coming. I have a question about color reflection. You were talking about nanostructures and color reflection. There was a picture of a butterfly there, and a butterfly wings, the color is not actually due to the pigmentation or hue, but it's actually a result of nanostructures that the wings possess. And these nanostructures are capable of reflecting electromagnetic spectrum, right, as you probably know. Is that the premise of this work, pretty much creating nanostructures that reflect a certain spectrum of electromagnetic radiation? And if, in fact, that is the case, then can you possibly learn how to reflect other segments of electromagnetic radiation as well?
Yeah, so eSkin, as I mentioned, was specifically focused on structural color. And Xu Yang, my collaborator on this, and now others at Cornell, are looking at this from a biomimetic standpoint to create entirely new materials that are programmable. So yeah, I mean, under a microscope at a nanoscale, this would look white, right? And we'd see these exquisite textures and geometries, and so we were looking at that sort of scale cascade and considering, together with human perception, how we might begin to translate that. And you're spot on. In current work, we're waiting to hear from the NSF any day for our phase 2 of a project that's focused on developing a bio-inspired mechanically tracking solar collection skin called HelioSkin. I can't show any of that, unfortunately, just yet. But in that project, we, through all of our user interviews, discovered a potential new application with farming and selectively filtering for particular wavelengths for particular crops. So we're looking at that right now. And it's still with the same concepts, right? And bringing our skills and methods with DigiFab to create assemblies where we can have bespoke angularity through 3D printed components. So you have sort of scales of difference and variation relative to different contexts, whether it's humans, plants, or just inspiring people to stop and have a chat. Great questions.
Thank you so much, Jenny. Great way to kick off this event. We're
It's an
now
honor.
going to have a closing reception at the exhibition, so you can see Jenny's work and the amazing work of all the participants across in the Double Ground building, excuse me, the Simpson Family Makers building, on the second floor in the Novak Gallery. So haven't had a chance to see the exhibition, be prepared to have your mind blown. Tomorrow, we'll kick off at 10 a.m. with day 2 of the Symposium. We'll have 3 panels. The gallery will be open in the afternoon, 12 to 4 tomorrow, so it's another opportunity to get in there. And I'm sure once you go in, you'll want to go back. But tomorrow will be the last day to go back, so you're really ahead of us. Thank you all for coming. Hope to see you all tomorrow. CCA architecture students repeats.
Try it. Salt sounds.
We also really do say.
So do you think it's common or could be